impact of organized data. Yeah. Here I want to address one problem. Yeah. If, remember I mentioned one idea before, if we are willing to put some investment to organize our data, to make our data structured, put some nice structure on our data, then later we can take advantage of the nice structure to make our operation faster. That idea. So this topic, I want to use one simple example to show you this idea. Yeah. All right, let's look at our computing problem number 6. It's called element uniqueness problem. Okay, yeah. So let's look at the question first. Yeah. Given an array, yeah, unordered array, how to check if all the elements are distinct? Simple question. Yeah. How to check? Yeah. Find a way. Yeah. So we have many different ways to do it. Yeah. You can use the brute force method. Then you can do something special. Then you want to make your new method faster. Yeah. All right. First, the method 1, brute force method. Yeah. Do nothing. Just do the checking. Okay. Yeah. All right. So here, do nothing here, it means we do nothing to organize data. We don't want to spend any computing resource to organize our data. Yeah. Yeah. We want to save. Yeah. We want to save some computing resource. Yeah. All right. So no cost in the data organizing step, no cost. Okay, all right. Then let's do the comparison. Now, in order to check, so here you only have 2 cases you want to identify. The first case, the elements are not unique. Then you need to find 2 of the elements in the array that are the same, right? Same value. Yeah. That's the first case. Second case, all the elements are distinct. Uniqueness. You have the uniqueness in this array. Yeah. Only these 2 cases. Right? All right. Then, to do that, yeah, here, we use comparisons to do that. Right. So there, you need to, so our first, because it's brute force method. It is a brute force method. We just do it in a straightforward way. Yeah. And we use several steps. The first step, we want to see if the first element is repeated somewhere else. Yeah. There is a possibility the first element, that same number appears somewhere in other elements. So first time we check if the first element appears in later positions, any of the later positions. Okay? All right? Yeah. Then to do that, you need to do all the possible comparisons, right? Yeah. You need to compare it with the next element. Then, one by one, like that. And at the end, you need to compare with the last element. Yeah? See? You need to do n-1 comparisons. That's only you do the checking on the first element. After that, you need to do the same thing on the second element. Second element, does it appear somewhere in the later positions, right? So you need to do the comparisons in this way. Comparison, and so on, okay? The last one. Then the second element, then third element, fourth. Then at the end, you need to go through all the elements. Yeah. That's the brute force method. Yeah. So in this brute force method, yeah. Now let us count the number of comparisons. We need to do the counting. Okay. All right. When we work on the first element, n-1 comparisons. Second element, n-2 comparisons. n-3, and so on. Okay? Second to last element, one comparison, right? The second to last with one comparison. Last one, no comparison. Only one left. No comparison. Yeah. So you add up all these n-1 numbers. Yeah. Yeah, 0. Yeah. So, all right. But here, we need to look at the best case, worst case efficiency. Best case, when you do the first comparison, these two elements happen to be the same, then you're done, right? Because your function return, yeah, so here, let's say element uniqueness. So here, let's assume our desired property is the element uniqueness. That's our desired property. So we make uniqueness case as 1. The function return value 1. Yeah, because we hope to see the elements in this array are unique. Yeah, so we set function return value 1 for the uniqueness case. Yeah. All right. Then the other case, not unique, duplicate. Yeah. Some element is duplicate. Yeah. That case, function returns 0. Okay? All right? Then the best case, when you compare the first two elements, same value, so the function should return 0, yeah, because it's not unique. Okay? Duplicate. Yeah. Not unique. Then you return a 0 value, then the function terminates, right? Yeah. After function terminates, you only do one comparison. Okay? So that's the smallest number of comparison. So that's your best case. Best case, one comparison. Okay? This is the best case, one comparison. Then worst case. Yeah. Worst case. Worst case, you need to do all the possible comparisons, right? Yeah. The largest number of comparisons you need to do for all the possible inputs. That's the worst case. Yeah. All right? Yeah. So let's look at for this case. Yeah. This special input. Okay? So you need to do all the possible comparisons. And after the last comparison, you detect those two elements are the same. Yeah. That's the function 0 case. You return function 0, but you need to do this many comparisons. Add up all these number of comparisons. So the worst case number is this number by our summation formula. Okay? Yeah. Yeah. So at this point, so everyone should memorize the summation formula. Yeah. Okay? Yeah? Yeah, last time still one student asked me 1/2. Remember that 1/2. Recall when I explain, I mentioned that area of the trapezoid. Yeah, in geometry, how do you calculate area of trapezoid, right? So you have that 1/2. Yeah. Right. Although here I can derive that formula, all right? So yeah, because to derive that formula, it's pretty simple. Yeah. So here, let me show you one smart way to derive this formula. You can see why we needed that 1/2. Why we need that 1/2. Okay? All right. Here. Oh, I should write here. Yeah. Because our goal, we want to add 1. We want to add 1 plus 2 plus 3 plus m minus 1 plus m. Okay, that's our goal. Okay, all right. Let's assume this number should be S, summation of these n numbers. Then, the smart way in math, there is some nice property. We can take advantage of it in problem solving. That property is the symmetry property. Symmetry property in math, symmetry of our data. So here, these n numbers, it's our data. Okay? In this data, can you see the symmetry property? Symmetry property, yeah. Very nice property. We should take advantage of it. Symmetry property, okay? Yeah. What kind of symmetry? Okay, yeah. 1 plus n equals n plus 1, right? 2 plus n minus 1 equals n plus 1. 3 plus n minus 2 equals n plus 1. Can you see if we pair the elements in this way, we get something like symmetry, right? Yeah, something like symmetry. What kind of symmetry? Okay. So you draw a line in the middle. That's our symmetric axis. Okay. So we flip, two sides flip, match. That's the way we pair our data. We use the symmetry way to pair our data. Okay. Then you see some nice property. The sum of the pairs of numbers, same number, n plus 1. So we should take advantage of this property. After you observe this property, next, you want to take advantage of it. How to do it? Yeah, so here, let me show you one special way. We take advantage of this property. All right. Second time, we write this S. Second time, okay? The second time when we write it, we reverse the order, okay? We reverse the order. Yeah, that's the same thing, right? So we write n first, then n minus 1 second in this reverse order. 3, 2 plus 1, okay? That's the same thing, right? Just reverse the order. After that, yeah, because after we write in this reverse order, we have two copies of S, double, okay? We double it. We double the sum. We double the sum. When we double the sum, now you can see we can apply that symmetry property here, okay? We group 1 and n. How about that? 2 and n minus 1 in this way, right? 3 n minus 2, group in all these pairs. Each pair n plus 1, right? Each pair n plus 1. All the way from beginning to end. All the sum of the, two numbers in each pair, the same number n plus 1 from beginning to end. How many pairs do you have? How many pairs do you have total? n pairs. Yeah, n pairs. Yeah, so here, n pairs. Each pair, the sum of two numbers, each pair n plus 1, but the total sum, 2 copy of sums, right? 2s. The total copy, you have 2s, not 1s. Yeah, but your goal, you want to find the s. Then you divide it by 2. That's the reason you have 1/2. That's the reason you have 1/2. Okay? You double it. Yeah. Double it.
You just mathematically prove why
Yeah.
some
Mathematically correct.
and you have 2 separate formulas for the 2 separate expansions for the best case efficiency and the worst case efficiency.
Here, we only work on the worst case efficiency. Best case, trivial, right? Yeah, trivial 1. So in this formula derivation, we don't look at the best case, okay? We only look at the worst case. Yeah.
Which is n minus 1 plus n minus 2.
Right, yeah. Because we have n minus 1 operands, right? Yeah. So that's why we do not use that. n minus 1, then plus 1. Yeah. All right? So here, yeah, because last time still some student asked me about this formula. So today I use some time to explain how to derive it using problem solving. Here you can see, yeah, some smart technique, right? The symmetry property, yeah. So your observation is important.
So what is, can you explain what again is symmetry? What's the symmetry we're supposed to be looking for?
Symmetry property, we take advantage of this property, we can find a smart way to calculate the summation. That's the whole point. Okay? Whole point. Yeah. All right. Yeah. Yeah. So let me continue our discussion. Yeah. So we finished the best case and the worst case. All right. But at the end, when we do final, because here, this is our method 1, brute force method 1. Then we will have a method 2, okay? When we do comparisons, we want to compare both worst case. We want to compare on the worst case part, the worst case. Yeah. All right? Yeah. We want to do fair comparison. Here, the fair comparison, we want to use the worst case to do the comparison. Okay? Yeah. All right, let's go to method 2. Yeah. Method 2, now we take a different strategy, problem-solving strategy. Okay? So I want to get to the point. Yeah. All right. All right. We pay some cost to organize data. So this time, this different strategy, different approach, we are willing to spend our computing resource to organize the data before we do the comparisons. That's the idea. Yeah. We do some preparation. Yeah. Let's do some preparation work. Yeah. Then we do the comparisons. That's the new strategy. Okay? All right.
It's going to be a faster strategy, right?
Could be faster. Yeah, we need to see. Okay? So here we treat that preparation step as the investment in our data structure. Yeah, why data structure? Because we want to make our data organized. We want to change the structure of our data from unorganized to organized. Now, that's the benefit of our investment. So why you do that investment? We make unorganized data to organized data. Okay? Yeah? So that's the immediate benefit. Yeah. All right. So we sort the array first. Yeah. Before we do comparison, let's sort it. How about that? Do the sorting. Okay? That's a lot of work, right? Sorting. Yeah. Last time we learned selection sort. Yeah. And I said that sort very slow. Yeah, very slow. So it's not a good sorting method. Yeah. So in the real world situation, definitely we don't want to use that selection sort. Nobody wants to use that. Too slow. Okay, real world. So here, here we imagine it is a real world situation. So we want to pick the best sort we know, right? Yeah. The best sort people know. Yeah. So for us, we haven't learned. Yeah. Because I said we will learn total 6 sorts. Yeah. We haven't learned that. Yeah. So later, after we complete this semester, you know all those 6 sorts. Now we want to pick the best sort in those 6 sorts. Okay? All right. That one, it will give us we need to use this many comparisons to sort. Yeah. The best one or the top one. Okay? Yeah. The top one. Okay? Yeah. Because there are several sorts in that list can give us this kind of efficiency. Yeah. N log n. N log n. Yeah. So that's the best we can get. So we are willing to pay or use n times log base 2. So here this log here, it's log base 2. Okay? Log base 2. Yeah. So this many comparisons, approximately, we know, because log base 2 of n may not be an integer. So approximately this many comparisons to get the whole array sorted. That's our preparation step. All right. Then, because how to see it, we will have a lot of discussion later. Yeah. So here we just use the result. Yeah. All right. The question, not the question. After that, we can do comparisons, right? So our next step, how to check if any element is repeated in this time we work on an ordered array. It's not an unordered array. Think about when we work on an ordered array, can we do much faster? Think about that question. So here we have an ordered array. Now you need to check if there are 2 elements with the same value. How do you check? Ordered, use this property because ordered property very useful. You need to use it. Okay? Yeah. So you need to you need to observe, find a nice property there. A nice property. Yeah. If 2 elements happen to have the same value in this ordered array, what should happen in this ordered array? 2 elements happen to be the same. You will see you can find 2 adjacent elements with the same value, right? 2 adjacent this time, because ordered. Okay? 2 adjacent elements. So this observation is important. That means you only need to do adjacent comparisons. Okay? Adjacent comparisons. Every time you just do adjacent comparisons. Okay? Yeah? The first method, you need to do all the possible comparisons, right? Yeah. So we can say in this way. In the first method, we need to do global comparisons. Comparison everywhere. Okay? Global comparisons. Second method, we only need to do local comparison. Actually, an adjacent comparison. Yeah.
So in this method, we don't care about the time it takes to sort.
The time we store it. Yeah. We will add this to our final time. Yeah. That's the time. Okay. Not that many comparisons. Yeah. Because we spend it, right? We spend it. We need to count it. Okay. We need to count it. Yeah. So that's why at this point, if the investment is worth it or not. At this point, we don't know, right? Yeah. We just know there is a different way to do it. Okay? Yeah. Yeah. Good question. Your answer at this point we cannot answer. Okay? Second one is better or first one is better. That question we cannot answer. So next class we will answer that question. Yeah. Right now, just two different methods. Okay? Two completely different methods. Yeah. All right. Yeah. So this time we only need to compare two adjacent elements. Yeah. This way, we can reduce the number of comparisons greatly. Okay? Yeah. Big reduction. Big reduction. All right. Yeah. So we use a simple for loop. Yeah. So do adjacent comparisons like this. Okay? Yeah. So this way, we only need n-1 comparisons. N-1 comparisons. Okay? Yeah. So the second step much faster. But don't forget, we need to add up the first number comparison in the first step. Now, two parts adding together. Remember last time I mentioned, when I skipped this topic, I mentioned this topic is very important in several questions in our homework and the tests. Okay? Yeah. So, yeah, we need to spend quite some time to understand how to solve this problem. So what's that? Finding maximum minimum. So this case, we want to find both maximum and minimum simultaneously. Not separately. Separately, very easy, okay? But simultaneously, then we need to do much more work.
In calculus, we call those critical values.
Critical,
In calculus, critical values.
oh yeah, you mentioned that. Oh yeah, now, but in calculus, it's different. We find so given a curve, you find the maximum, minimum, so you calculate the critical point, right? Use the derivative to calculate the critical point. Yeah. But here, in our computer science, it's different. Yeah. So we don't have a function that you can take a derivative. But that one, that's a curve, right? Curve, you can take the derivative. All right. So let me give you the question first. We are given an array with n distinct elements. Yeah. So here, for simplicity, simplify our discussion a little bit. So we assume distinct n elements. Question: how to find both maximum and minimum simultaneously? So what's that? Yes. Some student asked me to explain. What do you mean here? So here, I want to clarify the question. All right. You write one function, okay? Definition of one function. When you run this function, you need to find both maximum and minimum. So this function should produce two numbers, the maximum number and the minimum number, okay? It's not like this. You write one function, you run this function twice. The first time, maximum, second time, minimum. That's another way. No, it's not that way. Because you run the function twice. Then you need to use more comparisons, right? Yeah. But here, you can only run your function once. You can use fewer number of comparisons than twice. Twice because you waste your resource, right? Twice. Two separate times, some of the common resources are wasted, right? The second time, because the first time you derive some intermediate results, but you do not keep it. You throw away. So the second time, you redo it, right? So you need to do more work if you run it twice. Yeah. So here, we want to save our resource. So we don't want to waste our resource. So we only want to run it once. Yeah. That's the meaning of the question. Okay? All right? Yeah. So let us try to solve this problem. Yeah. Remember, I talk about one problem-solving idea before in our repeated squaring technique. I introduce one important idea in problem solving. How to find a better solution. At that time I said there is a very important idea. It's called reuse the resource. Remember? Reuse the resource idea. When you have some intermediate results, because they are useful, intermediate results are useful, so we treat them as our resource. So we should store our intermediate results for later use. That's the idea, reusing the resource idea. This time, this place, we need to use that idea. Okay? Or we need to find a smart way. So do not waste our resource. Or, try to manage our comparisons in an efficient way. Yeah, that's the idea. Yeah, that's one. Another also important idea I mentioned before, we could use elimination method. Remember? Elimination method. Yeah. And in this question, actually, the most important idea we want to use is the elimination method. Elimination method, okay? Yeah. Yeah. But how to do the elimination, that's hard. Yeah. Elimination, so how to do it in the right way, that is hard. Yeah. Yeah. Here, I want to show you. Yeah. You need to organize your data. Yeah. Organize your data to avoid redundancy. When you do comparisons, you want to avoid redundancy. That's the idea. Okay? All right. So let's look at analysis. Yeah. So we try to understand our data. Yeah. Here I use the notation. Okay? X1, X2. So these are n elements. Yeah. Distinct n elements. All right. Let us review elimination method. Yeah. Okay? Yeah. When certain elements do not satisfy the criteria, yeah, here I talk about the general idea. Because in your specific problem, you have special criteria, right? So here, maximum is one criterion, minimum another one, right? These two, okay? If some elements do not satisfy the criteria, yeah, it's just like if some of the elements cannot be the maximum and some elements cannot be the minimum, yeah, do not satisfy the criteria, then those elements, we can eliminate them from the consideration. Because after certain number of comparisons, you already know these elements cannot be the maximum. Yeah. Another group of elements cannot be the minimum. You already know. Can you safely eliminate them from the consideration? Yeah. Yes, you can. Right? Yeah. All right. Yeah. After the elimination, the data size is reduced, right? Yeah. The data size is reduced after elimination. Yeah. Yeah. But after the data size reduced, we can achieve better efficiency because we only need to work on fewer number of elements. We need to do less work. Yeah. That's our goal. We want to do it efficiently. Okay? Less work. That's the idea of elimination method. Yeah, here, yeah, in my discussion, I may use some concise notation. Yeah. When I do comparison, I like to write a pair of elements. Okay? Yeah. The comparison result, so this is the winner. Okay? Yeah. After comparison, yeah, we get a winner. Yeah. Yeah. So we get a winner. Okay? Yeah. All right. So I use this concise way. Yeah. So I do not need to write a lot of words. Okay? All right. Yeah. All right. The winner, yeah, because the winner is determined based on the requirement. Yeah. Yeah. Sometimes smaller one is the winner. Sometimes larger one is the winner, right? Yeah. But based on our intuition, yeah, most of the time we want to treat the larger one as the winner. Okay? The larger one, the default case, the larger one should be the winner. Yeah. Default case. Okay? Yeah. All right. Now let us do the data manipulation. Yeah. This time, how to organize data. Another important step, how to organize the data. So this time, I want to introduce another special method to manipulate the data. Yeah. It's called
Run multiple passes like through the data array, like for each element of the array, and every time we encounter a minimum or maximum, we just shift it to the beginning.
right. That's not efficient. Yeah. So you mentioned, yeah, multiple passes. Yeah. So here, since you mentioned that, let me quickly follow your idea to see how much we can get. Yeah. He said we can, run multiple passes, maximum, minimum. All right. So let's do that. We can treat that as a brute force method, right? That's the brute force because we do nothing special. Okay. Yeah. All right. Yeah. First time, let's find a minimum. How about that? Yeah. Minimum. How many comparisons do we need? Yeah. Find a minimum. We have that solution before, right? Let's apply that our old solution. Finding a minimum. How many comparisons? We have. Sorry. I should write here. On these n elements, how many comparisons? Finding minimum. Okay. First step. Minimum, we need n minus 1 comparisons, right? Yeah, that's our formula. Remember, optimality of algorithms, optimal, right? N minus 1. After we find a minimum, next, let's find the maximum. How many comparisons do we need? Maximum. Because the minimum cannot be the maximum, right? Because these n distinct elements. Yeah. And n greater than 1, let's assume. Yeah. I mean, if n equals 1, that's trivial, right? Yeah. We do not need to do anything. So we assume n greater than 1. Okay. After finding the minimum, we know the minimum cannot be maximum. Can we remove it? Can we eliminate it? After eliminate, we have one fewer element. So total element n minus 1. So then when we apply our old solution, finding the maximum, we need n minus 2 comparisons. So after that, you work on max, you need n minus 2. Okay? You add up these two steps, total, you need a 2n minus 3. Yeah, that's the brute force method. Okay? All right. Brute force method, this one. Now, I want to point it out. This way is not efficient. You waste a lot of resource. Why?
Does that mean it's like the way it's in the data is brute force, like way too efficient? It's too many.
Not necessary. Yeah. Most of the time, brute force not efficient. But remember our brute force last time, finding the minimum, that one, it's optimal. It's optimal. Yeah.
It's levels to this basically. Like it's
Yeah.
Sometimes it's the best, but other times like
Yes.
see if there's like something faster.
Right. Yeah. Most of the time we can find faster. Yeah. Here, all right. Because the first time when you find a minimum, you use certain number of comparisons after those comparisons, you get some intermediate results, right? Yeah. But second time, when you find a maximum, do you use all the intermediate results? No. You throw away. Then you start from scratch, right? You only do one elimination. After elimination, then it looks like all the comparison results, you do not need to use them anymore, wasted. So then you start from scratch, do new comparisons. The new comparisons may contain some redundant comparison. Redundant. Yeah. Because some comparison results are already known. Why you do another time? Right? So the problem is you may do a lot of redundant comparisons. That's the reason this method is not good. This method is not very efficient. We can do much better. Yeah. The way to do better, we remove those redundant comparisons. We want to avoid redundant comparisons. Yeah, so that's a great point. Okay, all right. Now I want to move to how to organize the data to help us remove the possible redundancy. That's the next step. We want to organize our data in a nice way. Then we can avoid redundancy. No redundancy. That's the best thing we can get. No redundancy. All right? So that's our new method. Yeah. The design idea of our new method. Yeah. All right. Now, grouping. How to group the elements. Yeah. How do we organize our data for comparisons? Using the grouping way. Group. Okay? All right. Group the data in pairs. In pairs. Yeah. Because in each pair, we can do one comparison. So that's the reason we want to group in pairs. Yeah. For comparison purpose. Okay? All right. Yeah. But when you do grouping, there are two cases you need to consider. Yeah. One case, you have, so when we do grouping like this, the question, we don't know if we can group all the elements in pairs, right? Yeah? So there is some uncertainty here. Yeah. Because we don't know if we have even number of elements or odd number of elements. We don't know it. Okay? Even or odd. Yeah. So here there are two cases. Even case and odd case. All right? When we have two cases, so in problem solving, many times we have multiple cases. Yeah. Here we have two cases, more than one. Yeah. So there is a common strategy, commonly used strategy in problem solving. When we have multiple cases we need to work on, we always work on the simplest case first. Simplest case first. Yeah. So later I will explain why this strategy helps a lot, because today I do not have much time. Okay? Today I just want to complete the solution. Yeah. Later, when I have more time, I will explain why this strategy helps a lot. Okay? Yeah. Here, can you tell me even case better or odd case better? Yeah. Easier case. Yeah. Easier for us. Even case easier or odd case easier for us? What do you feel? Even. Yeah. Because even all the elements can be paired. Okay? Without any singleton left. Odd case, there is one singleton left. So you need to do more work, right? Because you need to deal with the singleton. Yeah? Even case no singleton, so you just work on all those pairs. Yeah. So then we work on this even case first. So we assume there are even number of cases. Yeah. So here, So here, because our strategy, simplest case first. So here we consider n is even first. Yeah. Other case later. Okay? Yeah. So other case, after we get the even case, then we work on the other case. Yeah. All right. All right. So let's do the even case. Apply elimination method this time. Here, I like to introduce this tournament method. In sports games, tournament method. Yeah. So here, because we pair the players, right? Tournament method. Yeah. Round by round. Yeah. Yeah. Round by round. Yeah. Later we will do many rounds. Yeah. This one, yeah. So we just do one round. Yeah. Yeah. We do not do following rounds. Yeah. Later for other questions we will do many rounds. Yeah. So for the data, the size. Then we pair the players, even case this time. Okay? All right. Yeah. For the even case, so we do pairs like this. Yeah. We do pairs. Yeah. Do not block you. The first round, x1, x2 is the first pair. We do one comparison. Okay? x3, x4, second pair. Second comparison, okay? Then all the players can be paired, and we do one comparison between two players in the pair, okay? All right. Yeah. After that, then when we compare x1, x2, we have two possible cases, right? x1 is the winner or x2 is the winner. There are two cases, okay? When we compare x3 and x4, there are two possible cases. x3 to be the winner, x4 to be the winner. So each pair, there are two cases, right? Yeah. How many total cases? Yeah. Yeah. Two, because how many pairs? Think you have total n elements. Yeah. N elements divided by 2, right? We assume n even, divided by 2. So you have n over 2 pairs. You have this many pairs. So how many cases do you have? In counting, there is a method called a multiplication method. When you have, so here, all right, let me just ask you a simple question. Let's just consider if we have 4 cases, these four elements. First two cases. Second two cases. Total, how many cases? 4. 2 times 2, right? 2 times the multiplication. Here you use multiplication. 2 times 2, multiplication method. But now you have n over 2 pairs. Do you need to do multiplication 2 times 2 times 2? Total n over 2 times. Because you have n over 2 pairs. Right? Yeah. So the total number of cases you have, 2 to the n over 2 power. 2 to the n over 2. That many cases. Is that a big number? Is that a big number? Think about that. Power of 2 number, right? Exponent is n over 2. So it's a big number. Do you want to cover all the cases? Right? Nobody wants to cover all the cases. Too many cases. Yeah. So here, for this situation, So we cannot exhaust all the cases, right? Yeah. But here it's not necessary. It is not necessary to talk about, to discuss all those cases, because all the cases are very similar, right? All the cases quite similar, all right? If all those cases look almost the same, what is the simple way to do it? Large number of cases, but they all look the same, almost the same, right? From the form, from the outside form, they look almost the same, right? Yeah. In that situation, what do we want to do? Efficient way, we just pick one representative to discuss. That's enough. Pick one of this many cases as the representative to cover all other cases. How about that? One case enough. But this case, because this case can easily be converted to other cases. So this one is qualified to be a representative for all the other cases. And that's an efficient way. Okay? Let us pick that representative case. Okay? Yeah, here. The representative case, the first two, let's say X1 is the winner. That's because here we choose representative. Okay? We assume X1 is the winner. Because if X2 is the winner, no big change. We just flip two elements, right? So we get to X2 case. Yeah, we flip it. Yeah. No big change. Yeah. So that's why we can pick a special case as the representative. Yeah. All right. Yeah. All right. Efficient way. Select one typical case to study. Yeah. Typical case, yeah, assume X1 is the winner. Typical case, assume X3 is the winner. Typical case, yeah, so we assume the first element in the pair as the winner. Why we can do it? Yeah, because this one, from the structure, yeah, you can easily do conversion between two different cases, right? Yeah, flip. You just do some special way flipping, you can do the conversion. So if you can do on this one, then you can do on any case, right? Any case. Yeah. So that's the reason we choose this faster way. Yeah. All right, then. Here, sometimes we say, we assume these things without loss of generality. Yeah. We don't miss anything. Yeah. Because this case can cover all those general cases. Yeah, all those cases. Okay? Without any loss. Yeah. All right. Yeah. So here, if you after you understand that, because in our problem solving, many times we need to use this way. First, you need to identify it is this situation. After you identify it, you can use this way. You just select the typical case. All right. Then, yeah. All right. Yeah. So here, yeah. Yeah. Let's continue. Yeah. After that, yeah. So then, next step I want to talk about. Yeah. In this class, many times, because when we do our work, yeah, we want to. So here, when you write your solution, you want to make me understand quickly. Yeah. Because if you write a lot of words, a lot of sentences, I need to read, I need to understand. So very relatively hard. Yeah. So the faster way is draw diagrams. Yeah. When I see the diagram, I can visually understand your meaning immediately, right? I don't need to write a lot of sentences. Yeah. So use diagrams. That can save a lot of words. Yeah. So here, let me show you a diagram. Okay. The comparison result of the first pair, I draw this vertical bar, X1 on top, X2 at the bottom. That means X1 is greater than X2. So when you see this visually, you know the meaning, okay? One is higher, is greater than the other, okay? Similarly, for each comparison, we have this kind of, relationship. We can show relationship quickly, okay? All right, yeah. So after our first round comparison, we have n/2 comparisons, right? After n/2 comparisons, we get this result, okay? Yeah. So here, the data grouping. Next step, after this first round, now we need to do some processing work. Yeah. So this processing work here, I summarize as this data grouping way to do some organizing work, data organizing work, data grouping. Yeah. So usually when we do the grouping, we put the like elements in the same group. So those elements, if they share the same property, then we want to put in the same group because they are like, okay? In the same group. If they have different properties, so then we want to put in separate groups, right? So that's the usual way people do in the real world situation, right? Yeah. So when you organize your stuff, so you want to put the like items in the same group, right? Yeah. Here, same thing. Yeah. So when you look at all our elements here, all the elements, they have the same property. So we can put in the same group. Yeah. All right. So obviously, all these elements, because they are all winners, right? Yeah, that's their property. So they share the property. They are winners. They're all winners in their own comparisons. So we call this is the winners group. This is the winners group. Okay? The other half, they share the same property. They are losers. So we put them in the losers group. So that's what we call the grouping.
Okay? If this was it, would be called the losers club?
Whatever. Yeah. Things like that. Yeah. Yeah. It could be related. Things like that. Yeah. But hope to not trigger some, sensitive thing. Yeah. So here, all right. Then the benefit, when you do the grouping like this, the benefit is, so here, you can do the elimination very well. Because our goal, we want to do elimination method, right? Yeah. Think about what kind of elimination. I do not have much time, so let me finish this quickly. Yeah. All right. Because for the elements in the winners group, they cannot be the minimum, right? So when we calculate minimum, we do not need to consider winners group, right? Similarly, when you want to calculate the maximum, because all the elements in the losers group have no chance to be the maximum, right? So when we calculate maximum, we can eliminate losers group, right? When you calculate minimum, you can eliminate winners group, right? That's a lot of elimination, right? The more elimination you can do, the better you can do overall, right? Yeah, that's the idea. We maximize the elimination method. In this way, we maximize the elimination. Okay? All right. Yeah. So the final result, because I need to finish this solution quickly before the end of this class. Final result. Okay? All right. Yeah. That's the conclusion. Yeah. Yeah. So I already said these two sentences. Then we apply this observation to find a final answer. Okay? All right. Yeah. All right. Yeah. Just a summary. Yeah. But I need to give you the last solution. First round n/2 comparisons. Then, so let me try to finish. finish quickly. In 1 minute, I finish. All right. First round. Then second round, yeah, winners group, we need n over 2 minus 1 comparison to find the maximum. Okay? Yeah. Losers group, we need n over 2 minus 1 comparison for minimum. Yeah. Yeah. So this, after this, we get a max. After this, we get a min. Then we get both maximum minimum, right? Then let's calculate total number of comparisons. Yeah. Total, yeah. Adding these three numbers together, 3n over 2 minus 2 comparison. That's the solution. That's the final solution. Okay? Yeah. Yeah. All right. Yeah. Try to study it. Understand this solution well, because we have many questions based on this example. Several, okay? Yeah. Each assignment 2 or 3, something like that. 2 or 3 each. So that's many questions, okay? All right, that's it.